Let's talk about the sun. It's the big, bright ball of light you see in the sky almost every day. But it's so much more than just a light. The sun is a star. It's our star, the center of our solar system. Everything in our cosmic neighborhood, including our planet Earth, orbits around it. Think about that for a moment. Our world is constantly moving, held in place by the sun's incredible gravitational pull. It's a giant, fiery anchor for our entire family of planets, moons, asteroids, and comets. Without it, we would just be a lonely rock drifting through the cold, dark emptiness of space. So, how big and old is this star of ours? The sun is enormous, almost perfectly spherical, and mind-bogglingly massive. You could fit about 1 million Earths inside of it. It's so big that it contains 99.8% of all the mass in our entire solar system. That's why everything revolves around it. It's also incredibly old. Scientists estimate the sun is about 4.6 billion years old, born from a giant swirling cloud of gas and dust. It has been shining for a very, very long time, and it has enough fuel to keep shining for about another 5 billion years. That's a lot of sunrises. What is the sun made of? It's not made of rock or fire like a campfire here on Earth. The sun is a massive ball of superheated gas. This gas is mostly hydrogen, about 74% of its mass, and helium, about 24%. The remaining tiny percentage is made up of a mix of other elements like oxygen, carbon, and iron. The sun is so hot and its gravity so strong that deep in its core, hydrogen atoms are squeezed together to form helium. This process is called nuclear fusion, and it releases an astonishing amount of energy. That energy is what makes the sun shine so brightly and feel so warm, even from 150 million kilometers away. This incredible energy output is what defines the sun's role in our solar system. It's the ultimate power source. The light and heat it produces travel across space, warming the planets and providing the energy needed for all sorts of phenomena. From the weather patterns on Earth to the faint light that reflects off distant planets like Jupiter and Saturn, it all starts with the sun. It's a gigantic natural nuclear reactor in the sky, a constant source of power that governs everything we see in our celestial backyard. Every single day we are basking in the light of a star, our very own magnificent and life-giving star. The sun's importance to us here on Earth cannot be overstated. It is, quite simply, the reason life exists on our planet. Consider plants, the foundation of most ecosystems. They use a remarkable process called photosynthesis to convert sunlight, water, and carbon dioxide into chemical energy or food. This process not only feeds the plants themselves, but also releases the oxygen we breathe. Every animal, including us humans, depends on this chain. Whether we eat plants directly or eat animals that eat plants, the energy we use to live, work, and think can be traced right back to the sun. It's the ultimate source of our vitality. Beyond providing the energy for our food and air, the sun also keeps our planet at a comfortable temperature. Earth orbits the sun in a special region called the habitable zone, sometimes nicknamed the Goldilocks zone. This is the perfect distance where it's not too hot and not too cold for liquid water to exist on the surface. Without the sun's consistent warmth, Earth would be a frozen, lifeless ice ball, with temperatures plunging hundreds of degrees below zero. The sun's gentle, steady heating of our atmosphere and oceans is what makes our world a livable, thriving oasis in the vastness of space. The sun is also the primary driver of all our weather. It's a giant weather machine. The sun doesn't heat the Earth evenly. It shines more directly on the equator than on the poles, creating temperature differences. This differential heating causes air and water to move around the globe. Warm air from the equator rises and moves toward the poles, while cooler air from the poles sinks and moves toward the equator. This circulation creates winds, ocean currents, and the water cycle of evaporation and precipitation. Every cloud, every gust of wind, and every raindrop is a part of a complex system powered by solar energy. So when you look up at the sun, remember you are looking at the engine of our world. It provides the energy for the food you eat, the oxygen you breathe, the warmth that keeps you comfortable, and the weather you experience every day. Its light takes about 8 minutes and 20 seconds to travel from its surface to our eyes, meaning we are always seeing the sun as it was a short time in the past. It's a constant and powerful presence, a daily reminder of the intricate connection between our planet and the cosmos. It's the lifeblood of Earth, a brilliant star that makes everything we know possible. When we look at the sun, safely of course with special filters, it might seem like a smooth, unchanging sphere of light. But it's actually a very dynamic and active place with a complex structure. The visible surface we see is called the photosphere, which has a temperature of about 5,500 degrees Celsius. Above that is a thin layer of the solar atmosphere called the chromosphere, and above that is the incredibly hot but very thin outer atmosphere, the corona. Deep inside, the sun has a core where nuclear fusion happens, a radiative zone where energy travels as light, and a convective zone where hot gas bubbles up to the surface, kind of like water boiling in a pot. One of the most famous features on the sun's surface are sunspots. These are temporary dark patches that appear on the photosphere. They look dark because they are cooler than the areas around them, though they are still incredibly hot, at around 4,000 degrees Celsius. Sunspots are caused by intense magnetic activity, where the sun's magnetic field lines get twisted and poke through the surface. They can be as small as a planet or grow into vast complexes many times the size of Earth. The number of sunspots we see isn't constant. It increases and decreases over a regular period known as the solar cycle, which lasts about 11 years. These areas of intense magnetic activity can also unleash powerful explosions of energy. Two types of these solar storms are solar flares and coronal mass ejections, or CMEs. A solar flare is a sudden, intense burst of radiation, while a CME is a massive bubble of gas and magnetic field that erupts from the sun into space. When these eruptions are aimed at Earth, they can have significant effects. They can cause beautiful auroras, like the northern and southern lights, but they can also disrupt our technology by damaging satellites, interfering with radio communications, and even causing power grid failures. Scientists monitor these events very carefully. Flowing constantly from the sun in all directions is a stream of charged particles known as the solar wind. This wind travels through the solar system at speeds of over 1 million miles per hour. It's this solar wind that shapes the tails of comets and creates a huge protective bubble around our solar system called the heliosphere. Here on Earth, our planet's magnetic field protects us from the most intense effects of the solar wind, deflecting the particles around us. This interaction is what creates the auroras. The sun isn't just sitting there, it's actively influencing its entire system with winds, storms, and cycles. Even though we've learned so much about our sun, it still holds some profound mysteries that puzzle scientists. One of the biggest puzzles is the coronal heating problem. The sun's visible surface, the photosphere, is about 5,500 degrees Celsius, but its outer atmosphere, the corona, sizzles at temperatures of over 1 million degrees Celsius. This is completely counterintuitive. It's like walking away from a campfire and feeling it get hotter instead of cooler. Scientists are still debating the exact mechanisms that superheat the corona. Theories involve waves of energy or countless tiny magnetic explosions, but the complete answer remains elusive. Another major mystery is understanding and predicting the sun's activity. We know that the sun goes through an 11-year cycle of high and low activity, but the exact workings of this internal magnetic dynamo are not fully understood. What causes the cycle to be strong some decades and weak in others? And how can we accurately predict when a powerful solar flare or a massive coronal mass ejection will erupt? Being able to forecast this space weather is crucial for protecting our astronauts and our technology-dependent society, but our prediction models are still in their early stages. These are some of the biggest questions in solar physics today. To answer these questions, we are sending robotic explorers closer to the sun than ever before. Missions like NASA's Parker Solar Probe are flying directly through the sun's corona, touching the star to sample its particles and magnetic fields. At the same time, the European Space Agency's solar orbiter is taking the closest ever pictures of the sun and studying its polar regions for the first time. On the ground, new and powerful telescopes like the Daniel K. Inouye Solar Telescope in Hawaii are giving us incredibly detailed views of the sun's surface, helping us understand the small-scale processes that drive its massive events. Our journey to understand the sun is a perfect example of science in action. We have moved from thinking of the sun as a deity to understanding it as a star powered by nuclear fusion. We've mapped its structure, identified its features, and recognized its profound influence on our world. Yet for all we know, there is still so much more to discover. Every new mission and every new observation brings new pieces of the puzzle, sometimes revealing even deeper questions. The sun, our brilliant and life-giving star, continues to be a source of both illumination and wonder, reminding us that the universe is full of incredible mysteries waiting to be solved.